So, hey everybody, and welcome to my video on the introduction to logic. Now, this isn't the normal type of logic where Ben Shapiro is going to destroy you with facts and logic, but we're going to be talking about logic like the theoretical underpinnings of computer science. So, today we're going to go over some logic, and I thought some cool examples would be some Boolean algebra to really drive those points home. So right here I have the formula sheets for the logic and sets, and I purposefully chose the ones that have like the set identities next to them because I really like showing people how logic and sets are really two sides of the exact same coin. They're really very similar. And when you realize that, it makes working with sets a lot easier. So once we start learning about logic, maybe I'll make another video about sets if you guys want, and we'll see how they kind of go hand in hand. So let's start with an example. So here we are in the next clip, and I figured let's start off with some definitions. So whenever we see a bold T, that means that's the definition of true, the literal definition of truth. The same here with the bold F would be for false. And so what does P mean? P just means P. P can be either true or false. P has a value of P for right now. It's kind of like a placeholder. It's a variable. So also, a lot of people, when they're working with Boolean algebra or logic, they have different notations for negating. A lot of people use a bar. I'm going to be using the negation symbol, and that looks like this little sideways L. So not true would equal false, and that's what I'm showing you here. So let's move on to an example. And this, if you're familiar with the topic, is probably an example you may have seen before, but let's walk through it. We have P or Q implies R is equal to P implies R and Q implies R. So I guess let's explain what these symbols are too, if this is introduction to Boolean algebra. So this is called a V, this is called a wedge, and this is the symbol, this is the logical OR, and this is the logical AND. One silly way that I remember the difference is this is kind of like an exponential symbol, and like and multiply always go hand in hand in my mind. I don't know if that'll help you, but it's helped me. So whenever I try to tackle one of these equivalency problems, typically I'm going to grab one of the sides and I'm going to try to make either the left side look like the right side or the right side look like the left side. And we're going to manipulate it using these formulas over here. So I've already taken the liberty of writing out the first step for us, and I just copy and pasted this over, and I showed you what we can turn this into. So we could take the left side, and if we use the implication identity, which is this formula right here, it says that P implies Q. Well, that is the same thing as saying not P or Q. Alright, so by applying that formula, we have not P or Q, which is just the same thing that we had before. We just negated this whole term, and then this implication turns into an OR. In a later video, I'll go more in depth on implications. We're just going to stay kind of surface level for implications right now. So from here, how do we make this look like this over here. Let's copy this over. Well, we know that we need two terms. So actually, I think that the first thing we're going to do is distribute this negation. So when we're distributing a negation across like multiple terms, so I guess a good rule of thumb is whenever you're distributing inside of a parentheses, because typically you're not going to have a parentheses around just one term, you need to apply De Morgan's law. De Morgan's law tells us that when distributing, we flip the sign. So it's going to look like this. And instead of an or, this becomes an and. Now, we can take this portion, and now what I was saying before is we know that we need two terms, right? So we want to take this single implication, we were going to try to turn it into two implications. So what I think we can do is take this hanging or are term and distribute it across this tuple. And that would set us up to have not P or R and not Q or R. And that is starting to look a lot closer to this, especially if you remember how we applied the implication identity in the beginning. So let's see how we would do that. We would take this or R, and remember, here's a good rule of thumb. Here's how I like to remember how distribution works in my head. I'm distributing the operator as well as the variable here. So there's going to be two ors and one and when I'm done with this operation. So let's see if I can do this. Right here, and this will be gone. And we can clean it up with some parentheses like that. They don't match because Microsoft Word wants to be a little silly, but you get the picture. So now we're left with this, and as I already alluded to, we are going to apply the implication identity twice over, because just like we went from having an implication to turning that into just Boolean algebra, we are set up now to turn not Q or R into Q implies R and not P or R into P implies R. So let's do that. And there we go. And let's just do a quick recap so we can see what's going on here. So this first step is the implication identity. So I'll just call it implication ID. This step here is De Morgan's. This step here is distribution. And this final step is the implication identity again. Well, I hope you learned a little something in this video. And if so, give it a thumbs up and be sure to subscribe. Take it easy.